In this lecture, we will consider some numerical illustrations based on the notions and concepts of hypothesis testing that we have already come across. But before going into the actual numerical illustrations, we need to understand some prerequisites. So for that, we will consider binomial distribution in the first place and Poincare in the second. So binomial distribution. We will start with binomial distribution with some important definitions. First, we shall talk about trial. What is a trial? Suppose we repeat a random experiment sometimes, a number of times. Then each repetition of the experiment will be called a trial. Suppose we throw a die 10 times. That means the random experiment of throwing the die is being repeated 10 times. Each repetition of the experiment will then be termed as a trial. Next, we go to independent trials. A number of trials are said to be mutually independent if the result or the outcome of any trial does not depend on or influence upon the outcome of any other trial. We stick to the same example of throwing a die 10 times. Now you see, suppose in the first throw I get a 3. Then whatever I'll get in the second throw or third throw or in any subsequent throw, will that be dependent on what outcome I received in the first throw? No. In this sense, the outcome of the first throw is not influencing the outcomes of the subsequent throws. Similarly, the outcomes of the subsequent throws will not be dependent on the outcomes of the previous throws. In this sense, we can say that these trials are mutually independent. Now, why we studied trial and independent trial? That is because we want to come to the very important definition which is called Bernoulli trials. A number of trials are said to constitute a series of Bernoulli trials if they satisfy 3 conditions. Firstly, the trials have to be mutually independent. There will be exactly 2 possible outcomes with respect to each trial. We generally term them as success and failure. The probability of success and that of failure will remain constant in every trial. Now see, suppose the die we have thrown is unbiased. For simplicity, we are taking an unbiased die, but it may be generalized to any situation. Now we know for an unbiased die, the probability of getting any face is 1 by 6. Suppose we define success as getting a 6 in a throw and a failure as getting non-6 in a throw. So that means each throw, the outcome of each throw may be categorized in 2 ways, success and failure. Getting a 6, not getting a 6. The die is being repeated, the die has been thrown 10 times. That means the experiment has been repeated 10 times. So we have a number of trials and we have independent trials. Each independent trial has got 2 outcomes, success and failure. Now what is the probability of success? Probability of getting a 6 in any trial. The die being unbiased, the probability is 1 by 6. So the probability of success remains constant in each trial. And since the probability of success remains constant in each trial, so the probability of failure will also remain constant in each trial, which is 5 by 6. So that means here in this example, the trials are Bernoulli trials. The probability mass function of a binomial distribution. It is fx equals to ncx, p to the power x, q to the power n minus x takes the value 0, 1, 2 up to n and 0 otherwise. You can see there are 3 constants involved here, n, p and q. Now p plus q is equal to 1. That means p and q are basically, if I specify the value of p, the value of q can be obtained and the other way also. So basically there are 2 constants involved, n and p. These 2 are the parameters of this distribution and we use the notation x follows binomial np. There are several properties of a binomial distribution. A binomial distribution may be obtained as the probability of x successes in n Bernoulli trials. That means if we go back to the example that we have considered, if I say that x is the number of 6s obtained out of 10 trials, then x will follow a binomial distribution with parameters n equals to 10 and p equals to 1 by 6 because the die was unbiased. The expectation comes out to be np. So the mean of a binomial np distribution is n into p. The variance is n into p into q. Mode. Mode is that value of x for which the probability is maximum. In case of binomial distribution, two situations can arise. One is n plus 1 into p is not an integer. Then the mode will be at box of n plus 1 into p. Now what is box of n plus 1 into p? The greatest integer contained in n plus 1 into p. That means if n plus 1 into p is say 9.2, then box of n plus 1 into p will be 9. On the other hand, even if n plus 1 into p is say 9.9, then also box of n plus 1 into p will be 9. So it is not the rounded off value, it is the greatest integer contained in a particular quantity. The second situation is what? N plus 1 into p is an integer. So in this situation, there will be two modes. That means at two values of x, the probability will be maximum. One is at n plus 1 into p and the other one is at n plus 1 into p minus 1. A binomial distribution may be proved to be symmetric when p is equal to half. And there is a very important recurrence relation in binomial distribution, as you can see on the screen. Fx is equal to n minus x plus 1 by x into p by q into fx minus 1. Look at the values of x. X runs from 1 to n. That means if I put x is equal to 1, I can get it in terms of probability x is equal to 0, that is f0. If I put x equals to 2, then f2 can be obtained in terms of f1 and so on. This is why this relation is called a recurrence relation. Next, we go into Poincare distribution. The probability mass function of a Poincare distribution is something like this. Fx is equal to e to the power minus lambda, lambda to the power x by x factorial. Pay attention to the values of x here. X runs from 0, 1, 2, dot, 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 and 0 otherwise. Here lambda, the only constant involved, is the only parameter. Lambda is greater than 0. And we use the notation x follows p lambda. I'd like you to recall that a discrete random variable may take up two types of values, either finite number of values or countably infinite number of values. In case of binomial distribution, we consider finite number of values, and in case of Poincare distribution, we consider countably infinite number of values. There is a very important result that we have to remember. Suppose x follows a binomial distribution with parameters n and p. Now, if n is very large, that is, if n tends to infinity, and p is very small, that p tends to 0, such that np is finite, suppose this finite value is denoted by lambda, then x may be assumed to follow a Poincare distribution with parameter lambda. That means, if we try to explain this, x has got a binomial distribution. We start with this. Now the number of trials becomes very large and the probability of success in a single trial becomes negligibly small, such that the product of these two is finite. In this situation, we may assume that x follows a Poincare distribution. So that means a binomial distribution may be approximated by a Poincare distribution under such a condition. Some examples of Poincare variate. Number of defectives. Now see, suppose in a manufacturing process, we have many articles are produced. Do we find that most of them are defective? If I say that finding a defective is a success and not finding is failure, now there are so many items produced in a manufacturing process, so that means the number of trials is very large. On the other hand, the probability of success, that is the probability of finding a defective, is very small. So that means you see the conditions for a Poincare distribution are being satisfied. So this will be an example of a Poincare variate. Similarly, number of accidents, number of telephone calls, number of misprints. These are all examples of Poincare variate. That is, these are examples of a random variable that will follow a Poincare distribution. We come to the properties. There are not much properties, but important properties these are. Expectation of x is lambda, variance of x is lambda. That means for a Poincare distribution, both mean and variance are equal, which are equal to the parameter lambda. And the recurrence relation here is fx is equal to lambda by x into fx minus 1. You can see the range of x runs from 1 to up to infinity. Now we will come to some numerical applications of binomial and Poincare distribution in testing of hypothesis. In our previous lectures, we talked about some real-life problems. Can you identify them with any of these distributions, binomial or Poincare? We shall now try to work out some numerical examples with the help of binomial and Poincare distribution, as well as the concepts we have learned in our earlier lecture. Suppose a coin is tossed 20 times, landing on heads 6 times. Perform a hypothesis test at 5% significant level to see if the coin is unbiased. So that means if P is the probability of getting head in a single toss, then we are going to test whether P is equal to half against P is not equal to half. What sample do we have? We have tossed the coin 20 times. And we know that heads have been obtained 6 times. And the level of significance will be 0.05 as we are asked to test at 5% level. So we first need to write down the null and the alternative hypothesis. Obviously, H0 is the coin is not biased, or equivalently you may say coin is unbiased, and H1 the coin is biased in favor of tails. The important thing is to note here that we only need a one-tailed test as the alternative hypothesis says in favor of tails. A two-tailed test would be result on the alternative hypothesis saying that the coin is biased. So we have to calculate just the probability that it lands on heads 6 times. If it landed on heads fewer than 6 times, that would be even more evident that the coin is biased in favor of tails. That is why we will calculate only the probability that the number of heads is 6. Consequently, we need to add up the probabilities of it landing on heads 1 times, 2 times, all the way up to 6 times. Now here if x denote the number of heads obtained, then x will follow a binomial distribution. Under H0, the coin is unbiased, so it will follow a binomial distribution with parameters 10 and half. So we can easily calculate probability x less than equal to 6. That is probability x is equal to 1 plus probability x is equal to 2 up to probability x is equal to 6. And you can see this comes out as 0.58. We are now asked to perform the test at 5% significance level. That means if there is less than 5% chance of getting less than or equal to 6 heads, then it is so unlikely that we have sufficient evidence to claim that the coin is biased in favor of tails. So that is basically 0.058 that we obtain is nothing but the p-value of the test. We can see definitely that 0.058 is greater than 0.05, which is the level of significance of the test. So we do not reject the null hypothesis, we accept the null hypothesis because we say that we don't have sufficient evidence to claim that the coin is biased. Had this p-value been less than 0.05, the level of significance, then we would have rejected the null hypothesis. So you see one thing here, that on the basis of the sample observations, we are accepting H0 or rejecting H0. In this particular situation, we are accepting H0. Now, had the sample observations been different, we could have taken a different decision. That means if the same experiment is performed twice or performed by 2 persons, there will be different sample observations and obviously different decisions may be taken. We have to keep this point in mind. We go to the second one. Suppose you have a die and you suspect that it is biased towards the number 3. And so run an experiment in which we throw the die 10 times and count the number of 3 comes up 4 times. So we have to determine whether the die is biased. We define x as the number of times the number of 3 occurs out of 10 trials. Now see, this random variable will have a binomial distribution because here we will denote success as getting a 3 and failure as not getting a 3. So it will follow a binomial distribution with parameters 10 and p. So under H0, that is when we assume H0 to be true, then obviously p will be 1 by 6. But because under H0, the die is unbiased. P is the population parameter obviously, which is the probability of success in any trial. The null and the alternative hypothesis will respectively be p less than equal to 1 by 6. That is, the die is not biased towards 3 and the alternative will be p greater than 6. So here also we'll again have a one-sided test. Here we will use the significance level alpha as 0.05. So we will calculate probability x greater than equal to 4. So x greater than equal to 4 we can think of as 1 minus probability x less than 4, or we can simply calculate probability x is equal to 4 plus probability x is equal to 5 plus probability x is equal to 6 in terms of a binomial distribution, and you can calculate this will come out as 0.069728, something like this, and this is greater than 0.05, which is nothing but our level of significance. So here again, we cannot reject the null hypothesis and we cannot say that the die is biased in favor of 3 at 5% level of significance. Now again, I would like to point out here is that Suppose the die is actually biased, but here we are accepting the null hypothesis and claiming that the die is not biased. But even when the die is biased, we could have obtained this thing because whatever sample observations we have got, these same sample observations could have been obtained even when the die is biased. That means we have committed one kind of error. Now here we are accepting H0. Had H0 been false, can you tell me what kind of error we would have committed? So in this case, we have accepted H0. Now had the die been biased, we have committed an error. So what kind of error it is? It would have been type 2 error. So we could have committed this error. We go to the next one. We suspect that a coin is biased towards heads. When we toss the coin 9 times, how many heads we need to have before we are confident that the coin is biased towards heads at 5% level of significance? Here it is a different way we are asking the question. Here basically we are asking how many heads we should get out of 9 tosses. That means when can we be confident that the coin is biased towards heads at 5% level of significance? It's not that we are given the sample observations and we are taking a decision. Here we frame our decision in our mind and we are thinking how many times we should get the number of heads to arrive at that decision given a level of significance. If we are sure that the coin is not biased towards heads, then we can use a one-tail test with the null hypothesis p less than equal to half and the alternative p greater than half. We are given alpha equals to 0.05, 5% test. Now you can see probability x greater than equal to 8. If you can calculate this with the help of binomial distribution, it will come out as 0.01953, which is less than alpha. On the other hand, p greater than equal to 7 is 0.08984, which is greater than alpha. So that means, see, out of 9 tosses, if we get 8 or more heads, then the p-value is less than the level of significance. That means at that time we will be rejecting the null hypothesis. But if we calculate probability x greater than equal to 7, then the p-value is more than alpha, so we accept the null hypothesis. So that means minimum how many number of heads we should get to reject the null hypothesis? We should get at least 8 heads. This means that if 8 or more heads come up, then we are 95% confident, because we are testing at 5% level, so we are 95% confident that the coin is biased towards heads. And so we can reject the null hypothesis. We come to the next problem. Historically, a factory has been able to produce a very specialized nanotechnology component with 30% reliability. What do you mean by that? That is, 30% of the components passed its quality assurance requirements. The management of the factory has now changed their manufacturing process and hopes that this has improved the reliability. To test this, they took a sample of 24 components produced using the new process and found that 13 components passed the quality assurance test. Does this show a significant improvement over the old process? Let us first try to understand the problem. It's a very real-life problem, and you may be asked to solve many such real-life problems using statistics. So that means in the factory historically, the components produced are of 30% reliability. That is, 30% of the products are satisfactory. They meet the requirements. Now a new process has been introduced, and obviously the process is introduced in the view of the fact that the company hopes that reliability will increase. Now, how to test whether the reliability has increased or not? We have to resort to a sample. A sample of 24 items have been taken, and it has been found that 13 of them are satisfactory, that they have passed the assurance test. Now, whether 13 out of 24 is a proof that the reliability has increased or not, let us try to solve this problem. Here also we used a one-tail test. Suppose P is the proportion of satisfactory items. So here the null hypothesis will be H0 P less than equal to 0.35. Because we started with 30% reliability, so P less than equal to 0.35 will be our null hypothesis. That means the reliability has not increased. And H1 is P greater than 0.35. That is, the reliability has increased by introducing the new process. The P value we can compute, 13 out of 24 we can compute. Using binomial distribution, it comes out to be 0.04225, which is less than 0.05 if we take the level of significance to be 0.05. Now here the P value is less than alpha. So what we do? We reject the null hypothesis. Now here, what do you mean by rejecting the null hypothesis? Here, by rejecting the null hypothesis, we mean we accept the fact on the basis of the sample observations that the reliability level has increased by introducing the new process. Now here, I would like to remind you of one thing. You see, we have tested 24 articles. We could have tested some more, and we could have found that only 13 are reliable. The others are not. Instead of 24, we could have tested 50, and out of 50 items, we could have found that only 13 are reliable. Then the p-value would not have been less than alpha. It would have been greater than alpha. That means, since we are testing with a fixed sample size, whatever decision we are going to take, we are taking on the basis of that particular sample. So here, had H0 been true and we rejected H0, then we would have committed type 1 error. And here type 1 error would have been fatal, because introduction of a new manufacturing process means spending of a lot of money. So even after spending a lot of money, then we are committing some error. That means the process has not been well. So these are the fallacies, or these are some of the points that we have to be cautious about, and therefore the sample size is to be taken very carefully. We go to the next one. An existing make of car is known to break down on average 1.5 times per year. A new model is introduced and the manufacturer claims that this model is less likely to break down. 10 randomly selected cars break down a total of 8 times within the first year. We have to test the manufacturer's claim at 5% level of significance. It is more or less similar to the previous problem, but the setup is different. Here you see we have given the mean time of breaking down. So we take the x to be the number of breakdowns of the new model of car in a year. Since we have an average rate of the data is discrete, we need to use a Poincare distribution because average is given. So x follows a Poincare distribution with parameter lambda, where the value of lambda is given to be 1.5. So here we will test h0 lambda equals to 1.5 against the alternative lambda less than 1.5. Because if the new process improves the situation, then obviously the average number of breakdowns will be lower. We need to decide whether probability x less than equal to 8 is less than alpha. Because here probability x less than equal to 8 is nothing but the p-value of the test, alpha 0.05. So lambda t will be 1.5 into 10 because 10 cars were there, that is 15. And the p-value comes out to be 0.0374. That means the p-value is less than the level of significance. So we accept the alternative hypothesis that the average rate of breakdowns has decreased. So here also you can see rejection of the null hypothesis is a good thing. That means what we will try to do, the rejection of null hypothesis will be something big. In this way, we should frame our null and alternative hypothesis, because there will be several real life problems that you'll be encountering. And we cannot foresee what kind of problems we'll be encountering in future. So we have to set up our null and alternative hypothesis in appropriate manner so that rejection of null hypothesis is a big thing and committing type 1 error is very fatal.